Okay, so let's continue our discussion of support vector machines. Recall that we were trying to look at the problem of binary classification in RT, right? And specifically linear classification. And so that corresponds to the hypothesis class for which we have functions h which take value +1 if some A transpose x is greater than or equal to b, and -1 if A transpose x is strictly less than b. And we saw that the first problem that we looked at was learning this particular concept class. And the nice thing that we saw is that learning this particular concept class can be done fairly efficiently. In fact, there's a convex optimization algorithm that allows you to learn the concept class. In fact, when I say learn the concept class, wherein you can implement ERM in computationally efficiently, right? And we saw that finding the ERM for pack learning, not agnostic pack learning, but pack learning, corresponds to just solving the support vector machine problem, or the hard SVM problem, wherein you just find that A comma B that minimizes the L2 norm squared of A with the constraint that the yi times A transpose xi minus b is greater than or equal to 1 for all I. Right? Correct. This is a specific algorithm, right? The hard SVM problem reduces to ERM only in the realizable case, or in other words, only in the case where where the data set is linearly separable. So this algorithm in particular doesn't work if it's not linearly separable, right? And that's because you will not be able to satisfy all of these constraints. If it is agnostic, if you want to do agnostic pack learning, then you can't guarantee linear separability. Because if your data set is guaranteed to be linearly separable with probability 1, then it means that there exists a hyperplane that partitions the two sets, and therefore it means that you're only learning the concept class. Right? For agnostic pack learning, you need to be able to handle all possible joint distributions on x and y. So agnostic pack learning corresponds to the case where the data is not necessarily linearly separable. Agnostic pack learning, well, again, you have to be a little careful what you mean by the word strongest. If it is agnostic pack, so any problem, if it is agnostic pack learnable, then if you have an algorithm that lets you do agnostic pack learning, then you can also do pack learning. When I say pack learning, it's pack learning a concept class, right? So pack learning is a special case of agnostic pack learning, in the sense that agnostic pack learning is more general, right? So in the context of binary classification or linear classification, agnostic pack learning also corresponds to the case where the data may not be linearly separable, right? And in that case, ERM or hard SVM does not correspond to ERM anymore, because this particular optimization algorithm has constraints that cannot be satisfied if the points are not linearly separable. Great. And when analyzing this particular optimization algorithm, we saw that ultimately a solution does not depend on all of the data points, but only a subset of the data points, which we call the support vectors. And they correspond to all of those points that lie on the marginal hyperplanes. So even if someone threw out all of the data that do not lie on the marginal hyperplanes, you'd still end up with the same solution. So effectively, only those points are important, so to speak. Right? And then we did a little bit of basic analysis of the generalization error of these particular algorithms. So today what I want to look at is what happens if the data is not linearly separable. In other words, we want to go to the world where we're trying to do agnostic path learning. Right? So I introduce a modified variant of the hard SVM algorithm, what I call soft SVM. Right. So let me just write down the SVM algorithm. So what do you do? So compute the argmin of, or in other words, you want to minimize norm a square subject to the constraints that yi times a transpose xi minus b. Note that mod of a transpose xi minus b corresponds to the margin. This should be at least 1. Right? The yi essentially ensures that the sign is so this whole problem reduces to the problem of minimizing this such that the margin is at least 1 and the signs are always correct. Great. So the soft SVM algorithm is just a small is obtained by a small modification. So first I'll have two terms. So I want to not just minimize the norm of a square, but what I'll do is I will not be able to satisfy this particular constraint anymore, right? Because it may not be linearly separable. So instead I'll introduce a term. So I want to minimize the margin in some sense. So instead of having the constraint that this should be always greater than or equal to 1, I'll give a small slack factor of alpha I for each I. And I want to minimize the overall slack. And alpha I, but instead of minimizing the sum, I'll minimize some linear combination of those two. So this beta, you can think of it as a hyperparameter, right? You're just going to fix some arbitrary beta, and the quality of your output will depend on beta in some sense. Yeah, so there's one more constraint on alpha I. I'll demand that alpha I should be greater than or equal to 0 for all I. Right, so this is the soft SVM problem, and I'm going to minimize this over all possible A, B, and alpha. Okay, any questions? Okay. So this, as it turns out, is equivalent to the following problem. So argmin overall A comma B. Note that this is a constrained optimization problem. This is equivalent to the following unconstrained optimization problem. Norm A square plus 1 by n summation I equal to 1 to n of some function of yi, a, xi, and b, and this is going to be max of 0 and 1 minus yi times A transpose xi minus b. Right? So this second term was what is commonly referred to as the hinge loss. So the soft SVM problem can either be posed as this constrained optimization problem over here, or as an unconstrained optimization problem, which is basically a convex combination, which is a linear combination of the 2 norm of A the whole square plus this hinge loss. Okay. So let's sort of look at these terms a little more carefully. This is just a quadratic in A, right? 1 minus yi times A transpose xi minus b is just a linear function of A and B. What does the hinge loss look like? What is max of 0 comma something? Yeah. So or maybe again, depends on how you want to look at it, but what does max of 0 comma, let's say 1 minus x, what does this look like? It's equal to 1 minus x if it's equal to 1 minus x if x is if x is greater than or equal to greater than or equal to 1. Correct. So 1 minus x should be greater than or equal to 0. So if x is less than 1, then it's equal to 1 minus x, and it's equal to 0 for so is minus 1. X less than 1. So this is what the hinge loss looks like, and at least from visually you see that it's a convex function, right? So what is the composition of a linear function with a convex function? That's also convex. What about the sum of two convex functions? Convex. This overall function that we have over here is a convex function. So this whole objective function is a convex function of A comma B. Which is great because now I can use any convex optimization algorithm to solve this. I mean, you see that this algorithm, this optimization problem is already a convex optimization problem. So if this is equivalent to this, then it should also be convex. But first, let's see why these two problems are equivalent. Right? And that's fairly straightforward. So this is the original optimization problem that I had. Which one? We had hard SVM. Correct.
Is equally formatting some other.
Correct.
Is that formatting related to the advantage?
Not necessarily, right? I mean, the sort of reductions that we had from one to the other in the case of hard SVM, we didn't really make use of any Lagrange multiplier theory. Sometimes it's an art, right? And sometimes it depends on, well, so firstly, does it matter whether you're solving this problem or this problem? Not really. You can come up with a solver. Ultimately, you may have some kind of solver that can solve this this in a slightly more efficient fashion because you've tailored. Not necessarily, right? Solving this problem may not necessarily be more difficult than solving this problem. It ultimately depends on what kind of, say, black box algorithm you want to use to solve these. If you're using a generic convex optimization solver, a general convex solver, then really it doesn't matter whether you feed this or this into it. We'll see. Right? So one thing is, of course, since this does not involve any additional constraints, it in some sense allows us to analyze and visualize the problem better, right? And we'll also see one primary reason why I want to bring it to this particular form is now that this looks like some kind of an empirical risk, right? So really why I want to look at this problem rather than this problem is because now I can interpret this as some sort of regularized empirical risk minimization. This is also a regularized empirical risk minimization, but in this case, the alpha i's don't correspond to a risk, right? So I can't really interpret this directly as an ERM. Whereas this is really, you are trying to minimize, so this is just the hinge loss, which is a valid loss function. And this is the empirical risk, not with respect to the 0-1 loss, but rather with respect to the hinge loss. And I have an additional a quadratic regularization term, an L2 regularization term. So this is in fact just empirical risk minimization with a regularization. The loss function is hinge loss. It's not the 0-1 loss anymore. Of course, what I really want to do is minimize the 0-1 loss, but I'm not doing that here. So that's also an important point, because now Soft-SVM is no longer an ERM with respect to the 0-1 loss. But now I've introduced I'm doing it with respect to a completely different loss function. But the advantage that I get is that this is a convex optimization problem that can be solved efficiently. Right? And in a little while, we'll see more efficient ways of solving this. Right? Particularly because of this term, which looks like a 1/n times summation of a bunch of terms. All right. So right now we'll assume that we are fixing a beta, that this corresponds to an empirical risk minimization. I'm not going to try to look at different betas and find the best beta or anything of that sort. Okay, so first let's see why these two are equivalent. So let's look at this original optimization problem. Now these constraints are equivalent to saying that if I just rearrange the terms, then I require alpha I to be greater than or equal to 1 minus yi times A transpose xi minus b, and alpha I should be greater than or equal to 0. Right? If I just look at these constraints, for each I want these two to be satisfied, which is the same as saying that alpha I should be greater than or equal to this, and alpha I should be greater than or equal to 0. I can club these two constraints together into just one, right? And this is the same as saying that alpha I should be greater than or equal to max of 0, 1 minus yi times A transpose xi minus b. Okay. So let's go back to the objective function that we are trying to minimize. I want to minimize this over all possible a, b, alpha. So the first term does not depend on alpha, right? The second term depends on, it's a function purely of alpha. So let's fix a particular a comma b and try to minimize this over all possible alpha I, such that alpha I should be greater than or equal to this max. What do you think the minimizer is? The minimizer should be max of 0, 1 minus yi times A transpose xi minus b. Because anything greater is only going to contribute something more to the objective function. So this is our min over a, b, alpha, such that alpha I greater than or equal to max. Let me just try this. Our min, since I'm really interested only in the minimizer of alpha a and b, right? So this is min of overall possible alpha beta from a square plus 1 over n summation I equal to 1 to n alpha I, and this minimization is only over the alpha I which is greater than or equal to max 0, 1 minus yi times A transpose xi minus b, and clearly the alpha that minimizes this is, which you select each alpha I to be equal to max of 0, 1 minus yi times A transpose xi minus b. So this is just R min overall AB of beta times the 2 norm of A squared plus the hinge loss. Right? Okay. Now again, going back to these two different formulations, there are certain advantages of the first optimization problem over the second optimization problem. The nice feature of the first problem is that everything is nice, smooth, and differentiable. Right? The objective function is differentiable in a, b, and alpha. The constraints are just linear constraints in a, b, and alpha. This is great. So I can in fact use the Lagrangian formalism for the first optimization problem. I cannot do that for the second optimization problem because the hinge loss is not differentiable. Right? But that will not cause a serious impediment when we want to ultimately come up with an algorithm to solve this. But just to analyze the Soft-SVM algorithm, we'll first look at the first optimization problem, the first formulation of Soft-SVM. So it's a convex optimization problem, and so let's look at the KKT conditions. Yeah, I just want to know what the solutions look like. Recall that in the case of hard SVM, we solved for the KKT conditions to find out what the support vectors were. In this case, we'll try to find out on which of the xi's does the final solution ultimately depend on, or is there a notion of a support vector, and if so, what are the support vectors? All right, so what is the Lagrangian going to be? Going to be A, B, alpha, and I have lambda and nu. I don't need, fine, let me just call them nu. So this is just beta norm A square plus 1 by n summation I equal to 1 to n alpha I plus lambda I summation I equal to 1 to n lambda I times 1 minus alpha I minus yi times A transpose xi minus b plus summation I equal to 1 to n nu I times okay, so what are the KKT conditions going to be? Yep, the gradient with respect to A should be equal to 0. So what do I get? 2 beta gradient, just to denote that this is with respect to A, L should be equal to 0. To beta A, what else? Plus summation I equal to 1 to n minus lambda I yi xi. This should be equal to 0. Correct? So A is 1 by 2 beta summation I equal to 1 to n lambda I yi xi. So we see that even in this case, the final solution, the optimizing A, is going to be a linear combination of the data points. Great. Yeah, we also need to do it with respect to B, but what does that give us? Summation over I equal to 1 to n, or there's only one term, so B should be equal to 0. So summation lambda I yi, this should be equal to 0. Okay. I'm sorry? Which remaining 3? Correct. So we need to do that as well. But what do I get when I take the partial derivative with respect to, let's say, alpha with respect to lambda? Wait, sorry. Are you going to take the partial derivative with respect to lambda? You don't need to take it with respect to lambda I, right? Lambda or
alpha.
nu. You need to take it with respect to alpha. Yes, I agree. So what happens when you take the partial derivative with respect to alpha I? In that case, the gradient with respect to alpha, L, set it equal to 0. What do you get? One by n. Okay, so if you want to take the partial derivative with respect to each alpha I, okay, so then that would be a 1 over n times the all ones vector plus, so this is an inner product between lambda and alpha, minus inner product between lambda and alpha. So this is minus the lambda vector. So again, you're taking with respect to alpha I, so it's minus nu vector. This should be equal to 0. So lambda plus nu, this should be equal to 1 over n times the all ones vector. Or in other words, lambda I plus nu I should be equal to 1 by n for every I. Okay, let's go to the something more interesting. The complementary slackness conditions should be satisfied. So for each I, either lambda I should be equal to 0 or this quantity should be equal to 0. Right? So sorry? No, right? So lambda I times h of xi should be whatever, hi of x should be equal to 0. Yes, for every one of the inequality constraints, the Lagrange multiplier times the term should be equal to 0, which means that either lambda I should be equal to 0 or hi of x should be equal to 0, which in this case happens to be 1 minus alpha I minus yi transpose, right? 1 minus alpha I times minus yi times A transpose xi minus b should be equal to 0, or this is equivalent to saying that yi times A transpose xi minus b should be equal to 1 minus alpha I. Okay. Similarly, from this I get that nu I times alpha I should be equal to 0, which means that either nu I should be equal to 0 or alpha I should be equal to 0, right? Okay, so let's go back to the first condition. Now a particular xi is going to be a support vector only if lambda I is not equal to 0, right? That's by definition what a support vector is. So when is lambda I not equal to 0? If lambda I is not equal to 0, then 1 minus alpha I times this should be equal to 0, or yi times A transpose xi minus b should be equal to 1 minus alpha I.
The lambda is not
So how do we define a support vector in this particular case, in the soft-SVM case? We say that a vector x is a support vector, if a particular xi is a support vector, if it appears in the linear combination that gives you A. Alright? So by definition, a vector xi is a support vector if lambda I is not equal to 0. That's how we define a support vector in this case. Xi is a vector, right? It's one of the data points. So xi is a support vector if lambda I is not equal to 0. And lambda I is not equal to 0 can happen if lambda I is not equal to 0, then necessarily this second constraint should be satisfied, or yi times A transpose xi minus b should be equal to 1 minus alpha I. All right. Okay. So in this case, again, multiple things can happen, right? Now, so this need not lie on that marginal hyperplane anymore, correct? Just because this is satisfied, it lies on the marginal hyperplane only if alpha I is equal to 0. So I have yi times A transpose xi minus b should be equal to 1. Okay. So now there are two cases. Case 1 is alpha I is equal to 0, right? Which means that xi lies on the marginal hyperplane. There's another case. So if alpha I is not equal to 0, then what should happen? What can you say about nu I? Nu I should be equal to 0, right? And now so therefore what should lambda I be equal to? So it should be equal to 1 by n, right? So this means that nu I equal to 0 and lambda I should be equal to 1 by n. So you know exactly what the coefficient of xi should be equal to. It should be, so lambda I is 1 by n. So therefore the coefficient of xi is going to be yi divided by 2n beta. In these two cases we say that, yeah, so this lies on the marginal hyperplane, and in this case we say that the point is an outlier. Right? So in the case, so this is the scenario where it does not lie in the marginal hyperplane. So pictorially it looks something like this. You have a bunch of points. Let's say this is the hyperplane that we got. Let's say we put some more points with these 2 points here. Here. Now this is my hyperplane, the classifying hyperplane, or the output of my Soft-SVM. And the ones in blue are the marginal hyperplanes. So there are 2 kinds of scenarios which are support vectors. The first kind of support vectors are those which lie on the marginal hyperplane. All of these lie on the marginal hyperplane and they are going to be support vectors. Right? Now, this hyperplane is also going to be a linear combination of some more terms. So these vectors which lie within the or which are sandwiched between the marginal hyperplanes, or they're completely on the wrong side of the hyperplane. Right? So these are the points that are misclassified. All of these are outliers. I'm sorry? Yeah, even if they're within the marginal hyperplane, there are outliers. They're not misclassified. So just because it's an outlier does not mean that it is misclassified. The only point is that the vector A can be a linear combination of these points, of any of these outliers. Again, the support vectors are not necessarily unique, but all that I'm saying is that the vector A can be is in general going to be a linear combination of the points lying on the marginal hyperplane and any of these outliers. What it is not going to depend on are these other points. For sure, it's not going to depend on these points. Yeah. Where?
Like the 3x's which are on the other side.
No, alpha I is not going to be, so 1 minus alpha I is going to be less than 0. So alpha I is always going to be greater than 0. That is guaranteed. But 1 minus alpha I can be negative. So indeed, when 1 minus alpha I is, that's also maybe a good point, that when alpha I is between 0 and 1, the point is not misclassified, but it's an outlier. But if alpha I is greater than 1, then it's misclassified and an outlier. Right? So there are two kinds of outliers in this case. And in general, the vector A can depend on either kind of outlier. Exactly. So these points that you're sure of, they don't really determine the vector A. Because in any case, these vectors don't really determine what the minimum margin is. So alpha I is sort of a slack parameter.
For the outliers.
Correct, for the outliers.
If alpha is greater than 1, we have an outlier as well as it being misclassified.
Correct.
If it's between 0 to 1.
Correct. So that will correspond to, let's say, the point.
Between the two marginal.
The two marginal.
So only if alpha I is 0, we have a correctly classified.
No, so it could be classified even if alpha. So if alpha I is between 0 and 1, it's classified correctly, right? Because when is a point correctly classified? When the sign of yi is the same as the sign of A transpose xi minus b. Or in other words, yi times A transpose xi minus b is greater than or equal to 0. So if alpha is between 0 and 1, then no worries at all. It's classified correctly. But now it's within the marginal hyperplane, so your confidence is rather low. That's the interpretation. Any other questions? If alpha equal to 0, then it lies on the marginal hyperplane. Yeah, support. It's a support vector that lies. Yeah. Which one? The misclassified points alpha is going to be greater than. The motivation, well, suppose that your data set is not linearly separable. You want a computationally efficient way of finding a linear classifier. Right? ERM, if I wanted to implement the actual ERM with the 0-1 loss, I can't do it because it's computationally very intensive. So this is just, right at this point, it's just a heuristic algorithm. Right? Because we know that hard SVM does ERM and it can be. Exactly.
What is this?
This is just sort of a relaxation of hard SVM. That's it. It is not an ERM, but it works well. Right. So we're gradually going away from the framework that we were looking at in the previous course, wherein we wanted to do ERM all the time. Now, at this point, we can't do ERM. I mean, there are other results that you can prove that, in fact, you cannot do ERM for, say, agnostic pack learning computationally efficient. There is no computationally efficient linear classifier when the data set is not linearly separate. So we need a computationally efficient algorithm, and this turns out to be one that works well. Does that answer your question? And in fact, you can prove a lot of rigorous bounds. You can prove bounds on the generalization error, and a lot of analysis has gone into these SVM type algorithms.
After outliers, can we go back and print the values of alpha?
What do you mean tweak the values of alpha?
Let's say that okay, there are parameters which are kind of the marginal hyperplane. We can again change the values of
Not really, right? So in fact, alpha I, we also know what the optimal alpha I is going to be for a given a comma, for a given a comma b, once you fix the classifier, we know what the alpha I should be. It should be max of 0 comma 1 minus yi times a transpose xi. So that's fixed. Once you fix a comma b, actually alpha I is fixed. Any other questions? Okay. Okay, great. So now maybe we are going to take a bit of a detour and try to see how we can implement ERM efficiently, computationally efficient. Now, in principle, we could use any general convex solver to solve for Soft-SVM, but we're going to revisit some of the topics that we've already seen in the convex optimization course. So specific gradient descent type algorithms. So let's quickly recap gradient descent, and I'll introduce a variant which is stochastic gradient descent, which is more widely used in practice. So yeah. I'm sorry? It is not, right? Fact learning the hypothesis class? Yes. So in fact, if your data set is linearly separable, and I'll leave that as a homework exercise, if your data set is in fact linearly separable, then all of the alpha i's are going to be equal to 0. And that reduces to hard SVM. So in fact, soft SVM is a more general version than hard SVM. And therefore, since hard SVM is a pack learner for the concept class of linear classifiers, soft SVM is also a pack learner for the concept class of linear classifiers.
In this setup, when data is not
correct,
what kind of
the hypothesis class is always linear, right? Because the output is always going to be a linear classifier. If it's not linearly separable, then it's no longer the realizable scenario, right? So you're not learning the concept class anymore. Right? Learning a concept class is basically equivalent to the realizability assumption, and the realizability assumption for linear classifiers implies that the data is linearly separable. It's not an ERM anymore, right? This in fact happens to be an agnostic pack learner, although it is not an ERM.
It's some other algorithm which
is this is another agnostic pack learner, which maybe doesn't do as well as ERM, but still does pretty well. And again, that's something that we will not go into details in the course, but you can definitely take a look at the textbooks where they do give you bounds on the generalization error. In fact, here. Correct. So let's just look at this hinge loss function. What does the hinge loss look like? So this is what it looks like, and at what point does it intersect the y-axis? What is this point? One, right? Now let's look at the 0, 1 loss. The 0, 1 loss takes, so if x is positive, in some sense it's classified correctly, then the loss is equal to 0, and if it is misclassified, then it takes the value 1. So the 0-1 loss looks something like this. Correct. So the hinge loss is, in fact, it's an upper bound for the 0-1 loss. And in analyzing the generalization error of this algorithm with respect to the 0-1 loss, you crucially make use of this fact. So basically, if I get a bound on the generalization error of Soft-SVM with respect to the hinge loss, then I also get a bound on the generalization error with respect to the 0-1 loss. So therefore, it suffices to just analyze the Soft-SVM algorithm with respect to the hinge loss. But we know that Soft-SVM is an ERM, or a regularized ERM, with respect to the hinge loss. So then you can make use of the results that you have for regularized ERM algorithms for the hinge loss, and that automatically gives you a bound on the performance with respect to the 0-1 loss. So that's the general idea, but yeah, we won't get into the details of that. Okay, so let's recall gradient descent. Again, let's set up the problem. The problem is that we're going to look at unconstrained minimization of a convex function. So we're given some function f over Rd. In general, it could be some convex subset of Rd. Some function from Rd to R, which is convex. What's the definition of convexity? F of alpha x1 plus 1 minus alpha x2 is less than or equal to alpha f of x1 plus 1 minus alpha f of x2 for all x1, x2 in the domain. In this case, we'll just take this to be Rd and alpha in 0. So that's a convex function. Our goal is to minimize this convex function. Let's begin by assuming that f is also differentiable. In other words, the gradient exists at all points. But we'll see that that's not necessary. And in fact, to see why that is the case, we've seen different ways of characterizing convexity of functions. So this particular characterization of convexity says that a function f is convex if you draw any straight line joining 2 points on the curve. The function always lies below this straight line joining these 2 points. Right? So the straight line joining 2 points is always an upper bound on the function itself. Similarly, there's also another characterization by lower bounding the function itself. You recall what that is? Okay.
Take the tangent to 3 points.
Correct. So you take any point and look at the tangent passing through this particular point, then that always is a lower bound on the tangent is always a lower bound for the function. And how do you represent that analytically? Okay, so y, okay, that's, let's say f. So let's say that this is the point at which we're constructing the tangent. Let's call this point, say, x prime. I'm looking at the tangent at the point x prime. So f of x minus f of x prime is greater than or equal to gradient of f evaluated x prime. Fine. The inner product between this and x minus x prime, right? Or f of x is always greater than or equal to f of x prime plus gradient f of x prime x minus x prime. So f is convex if and only if this happens for all x prime. Yeah, so it's basically this vector transposed with this vector. Okay, but this is assuming that the function is differentiable. What if it is not differentiable? Yeah, the first one. But then if the function is not differentiable, does it mean you can't construct a tangent? No, you can't really do that. But okay, let's consider a specific case. Let's consider f of x equal to mod x, right? It's not differentiable, that's for sure. So a function of this particular form, at any point x less than 0 or greater than 0, I don't have to worry, because the function itself is the tangent. Whatever, this line is going to be the tangent at any point for x greater than 0, and this line is going to be a tangent for any point x less than 0. What about x equal to 0? Yep, so even if the function is not differentiable at some point, doesn't mean that there's no tangent. The problem is there's no unique tangent at that particular point. Right? There could be multiple tangents. But even in this case, what can I say about the tangent? It's still going to be a lower bound for the function. Right? So every tangent is a lower bound for the function. So another characterization of convexity, more general characterization than the previous one, is the following. So f is convex if and only if for every x prime in Rd, there exists some vector v that depends on x in Rd such that f of x is greater than or equal to f of x prime plus the inner product between v of x and x minus x prime. All right, and any such vector v defines a tangent, and it's called a subgradient. any such
There is V of x.
v of x. I'll just get to that. So any such v of x is called a subgradient. So by definition, if f is a convex function, then there is a subgradient at every single point, and the tangent that is defined by the subgradient is always a lower bound for the function. But in principle, as we see from this example, there could be multiple subgradients at certain points. Yeah. So I'm sorry, it should be x prime. Defined at the point where the gradient or subgradient is defined. So any such v of x prime is called a subgradient, and the set of all subgradients at a given point. So we'll denote that by the set of all subgradients at a point x prime. We'll denote this by del f of x prime. Okay. And this is called the differential set at x prime. I'm sorry? I am not sure what a differential proxy is. All right. And in fact, we'll see that just as you have gradient descent, you can effectively replace the gradient with a subgradient. Okay.
That is set up R into R.
Which one?
Del f of
Del f of x prime. So for every x prime, it gives you a set. It's not a function, right?
x of
Sure, if you could view it that way as functions from Rd to Rd, but it depends on how you are going to define it. Because, yeah, it's just a set of vectors. That's the best way to think about it. For every x prime, it gives you a set. Right. Okay, very good. So even if the function is not differentiable, you still have this particular characterization.
a particular point that
Yep, so if f is differentiable at x prime, then the differential set contains exactly one element, and it's going to be equal to the gradient of f evaluated at x prime. So you've seen gradient descent before. Basically initialize some vector x0 time step 0, and you perform the following iterations for a certain number of rounds or at some point until a certain convergence is reached, until some stopping condition. Let's say for capital T iterations, you run the following: xt equal to xt minus 1 minus some eta times the gradient of f evaluated at xt minus 1. So at each time step, you're sitting at xt minus 1, and then you evaluate the gradient, and you always travel in the direction of the negative gradient because that's where your minimum is going to lie. That's the direction in which your minimum is going to lie. And how much you move is governed by this quantity eta, which we call the step size. We're going to mostly focus on constant step sizes. So we'll assume that eta is fixed beforehand. All right. But we, at least for the purpose of this course, will look at a minor variant. So typically what do you do in gradient descent? You run this for a certain number of steps, and what do you output? You output xt, right? I'm going to do something else. I'm going to output not xt, but rather the average. T equal to 1 to capital T xt. Okay. So indeed, capital T is usually a better estimate. But as we'll see, this has certain other advantages, and we'll be able to analyze the performance of this version of gradient descent better. Okay. But I mean, at least intuitively, it would seem that even if this in some sense might be slightly worse than the variant of gradient descent that you're thinking about, but this also has slight advantages. For instance, again, we're looking at the scenario where capital T is like reasonably large. So even if, let's say, gradient descent doesn't converge because you chose a step size that's a little bit bigger, in the end, the algorithm will keep oscillating. So taking this average can sometimes help, because the average of the points that are oscillating will give you something in between. So this in fact can sometimes perform better than just outputting xt. Right? You could take the average of just the last few. I agree. Again, there are many different variants. We just look at this particular variant because it's fairly simple, and we'll see that this allows us to analyze the algorithm better. That's the only reason I'm looking at this particular variant. All right. Okay. Now, in general, you could also replace, instead of taking the gradient, if the function is not differentiable, you could also replace this with a subgradient. We'll look at it in a little bit, but in general, in many cases, again, there isn't a unique subgradient, right? It doesn't matter, you just pick one in most cases. Oh, that you will have to compute. So typically we're interested in functions that are simple. For example, in problems of machine learning, the functions that we are dealing with are either compositions of, let's say, linear with a non-linear function which is not differentiable. For example, let's take the hinge loss. Right? Right. Let's take this example. The problematic component is this function, the hinge loss. Right? Now, what do I need in order to evaluate the gradient or the subgradient this at any given point? Just by using the chain rule also applies to subgradients. I need the gradient of this function with respect to x, and I need the subgradient of this overall function with respect to a single variable. I know exactly what the hinge loss looks like over here, right? So the only point that is problematic is x equal to 1. I can choose any subgradient I want. So one example is subgradient correct. I'm not aware of any systematic way of finding all of the subgradients, but as long as you're able to find one subgradient, that's it. Like typically, in most scenarios, you would have a finite number of discontinuities, I mean, a finite number of non-differentiable points, and in most cases, this is going to be a boundary case of the function after a certain point. Right? So, for example, the subgradient at this particular point is equal to the gradient at, let's say, 1 plus epsilon. Another choice is the gradient at 1 minus epsilon. So in many scenarios, that's enough. You just evaluate the gradient at some 1 plus epsilon, x plus epsilon, or x minus epsilon. That usually will give you the subgradient. I'm sorry, can you repeat? Correct. Yeah, if it's differentiable, then the derivative or the gradient is going to be equal to the subgradient. There's only one subgradient at that particular point, so you don't have to worry at all. It's only at the non-differentiable points that you have to do this additional stuff. Okay. Right. Let me see. Okay, so this is gradient descent, and in general you can replace the gradient with a subgradient. That's what is commonly done. Just replace the gradient with the subgradient and run the same kind of algorithm. Maybe this is a good point to stop. In the next class, we'll look at we'll bound at what rate does this gradient descent algorithm converge. So in other words, if I run this for t time steps and I make some more assumptions on the function f, in the sense that the function f doesn't vary too quickly, and the minimizer is within some, let's say it's bounded, then we can get a bound on how far away you are from the point of minimum after t steps. And then we look at a variant. So this is all fine. So gradient descent works great when the function is convex. But even then, there is the cost of computing the gradient or the subgradient, particularly for a loss function of this form. right? This is in fact a sum of functions. And when you have a sum of functions, the gradient is equal to the sum of the gradients, which is fine. You can find the gradient at each point, but then the complexity of running the gradient descent algorithm in each step scales linearly with the number of data points, and that is computationally very expensive. So then you turn to randomized algorithms in order to get an estimate of the gradient at that particular point. In fact, we'd use what is called an unbiased estimate of the gradient, called a stochastic gradient, and use that as a proxy for the actual gradient itself. But then you can't give deterministic bounds on the running time of the algorithm. You can only give probabilistic bounds. Okay. So let's stop here. Continue in the next class.